cooking. Okay, I'm gonna make the assumption that all of you have at some point in your life cooked or helped cook, or at least have some concept of cooking. Okay, so we're gonna go real simple. I'm not gonna write anything down yet. Okay, so let's pretend we're having Thanksgiving dinner. So we host Thanksgiving in my family. It's like 50 people, and they all come to our house. Okay, and I don't cook much, to be fair. But we are gonna make green bean casserole. Do we all know what green bean casserole is? Did you say no? I love green bean casserole, but it's like a hit or miss thing at Thanksgiving, right? Some people love it, some people hate it. It's one of those things. We're gonna go real simple on our recipe, just for purposes' sake right now. And then you don't need to write anything down. You're just gonna think right now. Okay. So to make green bean casserole, you have to go to your pantry. And it's actually 2 cans. I did 3 last bell, but it's actually 2 cans of green beans. And it's 1 can of mushroom soup. Okay. Nope, you need to write down. Like, no need to write this down. This is not anything to do with chemistry, but it's our analogy of the day. And these together will make me my green bean casserole. It'll make me 1 dish of it. Okay. Yes, there's technically milk, and yes, there's technically pepper, and yes, you top it with a little crunchy onion things. But we're going real simple here. Okay. So again, I have 50 people coming to my house for Thanksgiving, and I need to make as much green bean casserole as I possibly can. Okay. So I walk to my pantry, go inside. And I look in my pantry, and for whatever reason, they must have had a sale, and I have like hundreds and hundreds and hundreds of cans of mushroom soup. For whatever reason, that's not true at all in my pantry, but let's pretend there's like hundreds of cans of mushroom soup. Cool. All right. So I walk over to where I store the vegetables in my pantry, and I have 6 cans of green beans. Tell your friends, how many casseroles can I make for Thanksgiving dinner? We all agree. What's the number? Wait, what did you do in your head? 6 divided by 2, right? You said, hey, cool. I have 6 cans of green beans. It takes 2 cans to make every 1 casserole. And I can make 3 casseroles. Assuming again that you have the endless supply of the mushroom soup. Well, maybe a different year for Thanksgiving. I walk into my pantry and I have 10 cans of mushroom soup and I have 4 cans of green beans. How many casseroles am I making? 2, right? Because it takes 2 for every 1 of them for the green beans. I'm going to have some extra mushroom soup, but I can only make up to 2 casseroles. And this is what I need you to think about what we are doing for chemistry. Okay. Essentially, that's what this unit is going to be. If I have this much of my reactant, how much of my product can I make? If I have this much of my ingredient, how much of my casserole can I make? Okay. So I want you to think of even our balanced equations almost as recipes. We could write our green bean casserole recipe as an equation, and we could say 2 green beans, and don't write anything down. You don't need to write this down. Seriously, like, this is just our backstory. Makes 1. I'm going to actually write it like it would be in chemistry. You'd combine them together, right? All right. I guess I should put a little 2 down here, right? GB2MS, right? Make it look more like an equation. But hey, there's an analogy for your little project we'll do on Friday. So 2 green beans plus 1 mushroom makes this. So again, like that's what cooking really is, very, very related to chemistry. Okay, so it goes together. Now, here's the problem. In cooking, we use like cups and we use cans and we use tablespoons. What's a chemist's favorite unit? Mole. All right, so we're going to treat our recipes, our equations in terms of moles, and that is the foundation of this unit. All right, that's our new relationship we're going to make. All right, so we'll do our vocab and then we'll do some practice. All right, so this unit is called, this is how you say it, Ivan, stoichiometry. All right, so stoichiometry is what this unit is called, or stoic for short. I tend to just write stoic because I get real tired of writing the word out. And what is stoichiometry? It is the study, so it's like a little small part of chemistry, of quantitative relationships. So when you see quantitative, your mind better go math. Right? Just like we were doing with the cans and the casseroles. Right? Quantitative math. Relationships between the amount of reactants used and the amount of products formed. And I know you're all gonna copy it down word for word, that's what we do. Okay? But again, analogy is, this is literally, if I have this many cans, how many casseroles can I make? Or conversely, if I need to make 5 casseroles, how many cans of green beans am I going to need? 10. How many cans of mushroom soup am I going to need? 5. All right. If I have 8 cans of green beans, how many cans of mushroom soup do I need to go along with that? Well, 8 cans of green beans is going to require 4 cans of mushroom soup. Okay, that is the relationship we are making. Yes, we're going to turn it into chemistry. Yes, we're not going to use cans and casseroles, but that is the way, like, you need to imagine in your world, in your mind, of how this is going to work. Okay? So with your friends, in the next little box over, there should be 2 equations, right? Sketch the little particle diagram. Use circles and squares and shaded. Talk to each other. Draw them out and show them balance. Show it, draw them like with little shapes to show that it's balanced. Go. Visualize it like we did last unit. I'm going to use colors. Drawing a little diagram like we did last unit. Which color? All right, so think back last unit. Okay? We started our balancing. One of the very first things we did was a little Skittle activity, right? And you took the little Skittles, and each color represented a different atom of a different element, and we balanced them on the table, right? So we pictured the little Skittles to represent atoms. And so when we were balancing, it was always about this many atoms on the left. I have to have the same atoms on the right. So in our first example, if I start with 1 red calcium, I have to end with 1 red calcium. If I start with 1 blue carbon, I have to end with 1 blue carbon. If I start with 3 green oxygen, I have to end with 3 green oxygen. And thinking about it in terms of atoms is great for balancing. Okay? But in the world, do we ever just have like 1 little carbon dioxide molecule or 1 little atom of aluminum? No. All right. You don't ever just have 1 atom of something. You can't even see 1 atom, right? Like, it's moles and moles of atoms that you can then physically see on your aluminum foil. Okay. So we don't ever have 1 atom of anything. Right? What's our favorite unit in chemistry? Moles. Okay. So when you balance them, most of you, I think, want to picture it as atoms, and that's great. Use that for the balancing part because you have to have balanced equations in this unit. But when a chemist looks at a balanced equation, we actually don't think of it in terms of atoms. We look at this equation, and that one that's there, we picture the word mole in between it. So kind of like our little recipe for our green bean casserole, it was 3 cans of green beans plus 1 can of mushroom soup. For chemists, in between the coefficient and the chemical formula, we visioned the word mole. So it's not just 1 particle of calcium carbonate. We picture it as a whole mole of them reacting. And it will make 1 mole of calcium oxide and 1 mole of carbon dioxide. But that is the key thing for this unit that you've got to get into your head. That when we look at balanced equations in here and we start doing this math this time, when you look at your balanced equation, your mind needs to pretend that the word mole comes in between the 1 or the 2 or whatever and the chemical formula. And then you need to treat it like a recipe, all right? The recipe for making water is 2 moles of hydrogen react with 1, that's a 1, that's a terrible one, react with 1 mole of oxygen, and they make 2 moles of water. So again, you need to look at your equations like recipes, and recipes in chemistry, we measure in terms of moles, okay? So our foundational relationship in this unit is going to be how they relate to one another inside of a balanced equation. So here's your second definition for the day, which is a mole ratio. And a mole ratio is going to be a conversion factor, and it's going to relate the amounts in moles, hence we call it a mole ratio, of any 2 substances involved in a chemical reaction. And so we take this back to our green bean, and please don't write the green bean examples down, okay? We talked about the fact that we could write our green bean as an equation. So it's 1 can of green bean plus 1 can of mushroom soup makes 1 green bean casserole. Okay. So a mole ratio for this one, I'm not using the word moles, we're gonna use cans, but you could think of it as, well, I'm not writing moles, so you start writing moles. It takes 2 cans of green beans for every 1 can of mushroom soup. We can all agree on that, right? That's the recipe for green bean casserole. We can get 1, and I'm just gonna call it green bean casserole. 1 green bean casserole takes 2 cans of green beans. And that's how the ratio you all were doing in your head. Now with cooking, obviously you were writing it in your head, okay? Chemistry, we're gonna write it out the way I make you always write it out. But if we look at a real equation, so let's look at the one for water, okay? Here was our balanced equation that you drew off to the other side. So here's our balanced equation. There's a lot of mole ratios you can write inside of just this one equation. We can say that to make 2 moles of water, how many moles of oxygen do you need? What's its coefficient? Oxygen, you would call it 1 mole of O2. Okay. It's gonna take a second. All right, so again, your mind with these equations needs to say the word mole is in between them. And you can relate any 2 of them that you want, okay? So we can take any 2 of them and make a conversion factor. And you gotta remember, conversion factors are just our fractions that we're gonna use. One of them's on the top, one of them's on the bottom. So every time 1 mole of oxygen reacts, you make 2 moles of water. Just like every time 2 green beans get put into our dish, we make 1 casserole, okay? We could also relate and say, oh, 2 moles of hydrogen have to react with 1 mole of oxygen. So in our process of making water, it takes 2 moles of hydrogen mixed with 1 mole of oxygen. Just like up here, it takes 2 cans of green beans to go with 1 can of mushroom soup. All right, and this is the relationship you're gonna have to get down. These are mole ratios. All right, and what mole ratios allow us to do is change from one substance to another. Right, so we can change between, and BTWN is my way of saying between, I just don't want to throw the word out, 2 chemicals. All right, so that's what mole ratios are going to allow us to do. It's going to allow us to switch from a reactant to a product. It's going to allow us to switch from one reactant to another reactant so that we can do this math and say, well, if I'm starting with this many whatevers, how much of my product can I make? I'm starting with this many cans of green beans. How many casseroles can I make? If I'm starting with this many moles of hydrogen, how many moles of water can I make? Right? This is our foundation of the unit, is this idea that in a balanced equation, everybody is related by moles. Okay? So we're going to write out the relationship here. We're going to start with the middle. So in the middle of that box is where you want to write this, because we're going to go in either direction. So our new foundational relationship of this whole unit, like in the rest of the year, is that I can take the moles of A, which is just some compound, some element, somebody in my balanced equation, and I can turn it into moles of somebody else. Yep, so this is our new relationship. It's honestly the only new real relationship you're going to learn this unit is how to relate moles of one thing to moles of another. Okay? To do this, okay, we use mole ratios. That's how we're allowed to switch them. Okay? You have to have a mole ratio. And mole ratios always, always, always come from balanced equations. And so this is the first relationship that we're going to look at. And it's honestly, like I said, the foundation of everything else we do in this unit. Right? So this is the middle part of it. We're going to build to it in a second. So let's do an example where we just worry about this conversion. All right, moles to moles. All right, so first example. So it says, consider the following reaction. Bless you. You have an equation. Right? Anytime you see the little lines, what do you think you're probably going to need to do? Balance it. Talk to your friends. Go. And when your table thinks you have it, check with the next table. It's a harder one to balance. Balance it with your friends, talk yourselves through, and then check with the table next to you, and then we'll see where we're at. It's a hard one to balance. That was kind of mean. Harder one. When your table thinks you have it, turn to the tables near you and see what they say. See if we can all agree on about something.
1, 1, 2, 2.
What do you guys say? 1, 3, 2, 3? What's curious? Not 1, 3, 2, 3? Alkali moles. That's a hard balance. All right, so this one I'll walk you guys through. And again, like I'm telling you, if you balance it wrong, but you do the math right, please realize you get the full math points on a test or a quiz. Just keep that in mind. But if you're not like on worksheets, if you're getting the wrong answer, always check your balancing. But on this one, what I would have looked at, I mean, initially I would have gone and put a 2 here because of the 2 on the left. Now, here's where the O's get interesting in the carbons. I have 4 O's here and only 2 over there. So I'd be tempted to put my 2 there. And the second I put a 2 there, what do I have to put here? A 2 for the carbon dioxides. So what I did in my mind when I was balancing it is whatever number I put here, I have to put the exact same number there because so that my carbons are balanced. So I literally in my head tried 1 and 1, that doesn't balance. I tried 2 and 2, that doesn't balance. But what if I put 3 and 3? If I put a 3 here and a 3 here, I get 3 carbons on both sides. And if you look at your O's, you have 3 plus 3, and then you've got 6. Right? But again, please realize that you don't get 0 points just if you balance it wrong. This is a hard one to balance. Yeah, so you always have to have a balanced equation. Okay? Always. And then we can start doing the math. Okay? So it says, back to our problem solving skills. It's been a little while since we've done them. It says, how many moles of carbon dioxide? So you all know how I do this. I box what it is I'm looking for. This unit's gonna be all moles and grams. We will not worry about Avogadro's number too often anymore, all right? So it says how many moles of carbon dioxide? So I like to write it off to the side as my checkpoint at the end. So I want moles and I want moles of CO2, carbon dioxide, are produced. So this is like, how many casseroles can I make if 0.85 moles of iron 3 oxide react? There's going to be our starting number. So again, this is very much like, how many casseroles can I make if I have 12 cans of green beans? How many casseroles can I make if I have 6 cans of green beans? How many moles of carbon dioxide can I make if I've got 0.85 moles of iron 3 oxide? All right, we're going to set them up like we always do. So write your number down, 0.85 moles. Don't forget to include the unit. It will pretty much be moles and grams, this unit. And then this is where it gets interesting. You need to write your chemical formula. This is the unit. And the reason why I have wanted you to write it all year long is so you don't get yourself mixed up when we get to this unit. So it's moles of iron 3 oxide. If I give you an equation, please don't write your own formulas. Please pick the chemical formula that just matches the name. Like, don't waste your time trying to cross your own charges. Pick the one that matches. We need one that has iron and oxygen in it. What's the only chemical up there in the equation that's got iron and oxygen in it? This one. That must be iron 3 oxide. So seriously, if I give you an equation, don't waste your time crossing charges and stuff. Just pick the one that matches the name. Okay. Trying to help you out here. All right. Think back. It's been a while, but what do we automatically have to write on the bottom? Moles of Fe2O3. All right. There's your setup. Just everything we've kind of done our entire lives in chemistry class. Here's where the new thing comes in. We can relate the moles of any two things inside of an equation. So in this equation, we care about Fe2O3 and we care about CO2. Basically, you're assuming that you've got all of this that you need in the world. And yes, you're making this too, but we're not caring about it in terms of our math calculations. But those are the two things we care about. So if we look at them from our balanced equation, you know, every time 1 mole, because remember, you got to picture the word mole in between them. Every time 1 mole of Fe2O3 reacts, we make 3 moles of CO2. That's what your equation tells you. That if I put in 1 mole of Fe2O3, I'm going to get out 3 moles of CO2. And we're going to use that to do our conversion. So we're going to take our moles of Fe2O3 and we're going to turn it into moles of CO2. And this is what I'm saying. This is the new thing. Taking moles of one thing and turning it into moles of another. And as long as they're in the same equation, we can do that. And it's really nice. When you go to fill in these numbers, all you do is look at their coefficient. What number is in front of CO2? In front of CO2? 3. So on the top, I'm going to put a 3. When I look at my balanced equation, Fe2O3, what number does it have in front of it? Guess what I'm going to write at the bottom? 1. And remember, the whole point of our setup is that these moles will cancel, top and bottom cancel. Again, the unit on the top should match what you're looking for at the end. And what are you going to do with these two numbers? Multiply. So 0.85 times 3, I get 2.55. We would keep 2.6 moles of CO2. So this would again be like, if I have 3 cans of green beans, I can make 1.5 casseroles. Okay. If I have 6 cans of green beans, I can make 3 casseroles. If I have 0.85 moles of Fe2O3, I can make 2.6 moles of CO2. Yeah. Now, that's going to be our foundation. And we're going to do lots of problems with those because we care about moles, right? But we've also got to put it applicable for when we do labs, okay? So when we go back to our lab tables, what unit do our balances measure in? Grams. Do they measure in moles? Not so much, all right? So when we start making this applicable and actually doing labs, because we'll do one on Monday, we'll have the Bunsen burners out on Monday. We'll do one next week, you're going to design your own, and do another one. We got lots. coming up in the coming days. The unit's only 10 days long, including the test, and we do 3 days worth of labs. All right, we've got to be able to relate it to grams. Okay. So I'll look at my first example, which one's which. All right, so back up here in our little ratio. Okay, this is our foundation. This is our new thing. But we already know that moles relate to grams, or we should know, because we've been doing moles to grams since October, all right, with elements. So at the end, once we turn it into moles, we can also then take those moles and we can turn them into grams, because again, this is where our little cooking analogy kind of falls apart, because in cooking, we don't really measure this way. But remember that we count our atoms with moles, right? But in terms of being able to weigh them, we have to have them in grams, okay? So we can switch from moles to moles, which is great, right? That's our new thing. But when it comes to making measurements in the lab, more often than not, we're going to need to turn our moles into grams so that we're able to actually physically see, well, how many grams did I make? Because I can't count my moles because they're too small, okay? Where do we look to go from moles to grams? Periodic table, all right? Technically, it's called molar mass. So it's your molar mass that you're using. But all we're going to do is look up at the periodic table. Okay. So we're going to do an example of this. We're going to take moles of our guy, turn it into moles of somebody else. That's our new thing. We're going to use our mole ratio to do that. And then once we're in moles, we can use our molar mass from the periodic table and turn that into grams. Okay. So let's look at our next example. I know I'm making you flip back and forth. All right, so iron 3 oxide also reacts with just plain carbon to form iron and carbon monoxide. What kind of reaction is that? Single displacement. All right, carbon gets to kick out the iron. All right, so we balance this one. I have 2 iron on the left, so I'll put a 2. I have 3 O's on the left, so I'm going to put a 3. That gives me 3 carbon, so we'll go back and I'll give a 3. It's the same ratio. Yeah. All right, it's got our equation. So this one says, how many grams of iron 3 oxide? And so again, I like to box because you got to keep track of, is it grams, is it moles? That's gonna be the biggest thing in this unit. How many grams of iron 3 oxide? I like to write it down. Again, please pick the formula that matches the name. Don't write your own formulas if I gave you an equation. That would be silly. Are needed to make 1.75 moles of iron. And there's going to be our starting number. Okay. So again, going back through our technique of problem solving that we have been using since August, write down your starting number. Okay. So we're going to start with 1.75 moles of iron. So here's where when you look at your problem, notice that we're starting with Fe, but at the end, we want Fe2O3. Okay, this is the whole point. This whole unit, you're going to switch substances. Every single problem, you're going to change from one thing to another. You can only do that in moles. Right? Conveniently, what unit are we already in? Moles. All right. So when you're in moles, remember, we can look at a balanced equation. That's what your balanced equation tells you. It tells us that 1 mole of Fe2O3 goes with 3 moles of carbon to make 2 moles of iron and 3 moles of CO. So for this problem, we care about this one and this one, because that's what the question's asking you about. Okay. So we do our setup. Again, walk through the same thought process we've done since August. What absolutely has to go on the bottom of iron? Okay, so it's got to go on the bottom. Here's your new thing. You can take moles of one thing and turn it into moles of somebody else. So for this problem, we're going to turn it into moles of Fe2O3 because that's what the question wants. All right. You don't have to pick. You just do whatever the question wants you to do. To make that switch, again, this is your new thing for the unit. All we do is look at the coefficients in the balanced equation. So we look for Fe2O3. It has a 1. So what am I going to put up top? A 1. I look over here. Fe has a 2. What's going to go on the bottom? 2. So we can switch moles to moles just by looking at coefficients. Okay. Then it's back to old stuff, all right? I have moles of Fe2O3 on top, but I want grams. And I hope we all know that moles and grams relate. When I do my next one, moles have to go on the bottom. And we can turn those into grams. Where do you look to find the grams of something? Periodic table, okay? So you would do 2 times 55.85, that's the decimal for iron, plus 3, you probably know oxygen is 16, maybe you remember that? That's what you type in your calculator, you never have to show me that, like ever, I don't need to see that. If you type that in your calculator, you should get 159.70. Moles are gonna cancel. So this is your new stuff, mole to mole. This is your old stuff, moles to grams. Okay. And then our units match. So cool. I want grams. I have grams. I bust out my calculator. And same rules apply as always. Start with your 1.75. Not negative. Random. Bottom means what do you do? Divide. Top means multiply. And I got 139.73, blah, blah, blah. 1.75 has only 3 sig figs, so we'll keep 3. So we'll do 140, drop the decimal on there so that it counts Fe2O3. And for those of you that are thinking about significant figures because it's been a while, these are exact. Your coefficients from your balance equation are exact measurements, right? They are an infinite amount of significant figures. That's exactly how many have to react. Okay. Now, just as easily as we could end in grams, all right, what could we start with? Grams, right? So we go back to our little order of things. All right, so flip back to your first page. Way back here, we don't necessarily have to start with moles. Okay? And again, when we do our labs, you're not going to start with moles. You're going to go in the back and you're going to measure out grams. So you're going to, first lab, you're going to measure out grams of baking soda. Actually, the second lab, you're going to measure out grams of baking soda and do a different reaction. And the third lab, you're going to measure out grams of 2 different things. Okay. So again, there's lots of combination or like lots of different conversions we can make. But the big one in chemistry is going to be, I'm going to start with grams and I'm going to end with grams. Okay. So I can start with grams over here. And I can turn that into moles. And again, this is back old stuff. We're going to use molar mass. Where do you look for the grams of things? On the periodic table. Okay, so just as easily as starting in moles, we can also start with grams. And if I give you grams at the start, you have to take those grams and turn them into moles before you can use your balanced equation. Because again, your mind needs to be saying, my balanced equation tells me moles, tells me moles, tells me moles. Okay? So we'll look at our third example. There. So this one says sulfur trioxide decomposes to form sulfur and oxygen. Turn to your friends and balance this one. They'll probably go much faster. Do your O's than do your S. Much better one to balance. You're like, please give them all like these. What's our balancing? 2, 2, 3. You gotta get your O's both the 6 and then fix your sulfur. Okay, so you have to have a balanced equation always. Okay, and then again, remember in your mind, you need to be saying, oh, that's 2 moles of SO3. It makes 2 moles of S. It makes 3 moles of O2. That's what your mind needs to say. Okay? So when we read our problem, this one says, how many moles of oxygen? So I like to box what I'm looking for, just like to make sure I know what I'm trying to find. Okay? Like I said, it'll be all moles and grams for the most part in this unit. So I want moles, and I want moles of oxygen. And please remember, oxygen is O2. Okay? Are produced when 50 grams of sulfur trioxide reacts. I guess this would be kind of like asking how many casseroles can I make from like 50 grams of mushroom soup cans, I guess, would be kind of like what you would do. It'd be an odd way to do it. Alright. But again, we've been doing conversion since August, so walk yourself through our thought process. Write down your starting number. 50.0 grams. And then again, don't try and write your own formulas. It's sulfur trioxide. Look up at the equation. Which of those three things is sulfur trioxide? SO3. Okay, so don't write your own formulas if I give you equations, but that would be silly to do. All right, so again, let's walk ourselves through the thought process here. All right, I'm starting with SO3, my reactant, but I care about O2, my product. I've got to switch them. I can only switch when I'm in moles. Okay, that's the only time you can switch compounds is moles, because that's what our balanced equation tells us. So if I've got grams, the first thing I have to do is get rid of the grams. So I'll do my conversion. Grams of SO3 have to go on the bottom. Grams turn into moles. All right, maybe you want to write this down, but when you do grams to moles, you have to have the same chemical formula. Can't switch it there. It has to be grams of this compound is this many moles of the compound or element. We look on the periodic table. Sulfur is 32.06 plus 3 times 16 for the O, that's 80.06. And again, you never have to show me that. And every time we use the periodic table, since the first time we've ever used it, moles gets a 1. So at least we got to moles now, but we're moles of the wrong thing, okay? So old stuff gets us to moles. Now we can take moles of one thing and turn it into moles of another. That is the foundation of stoichiometry. I can take moles of SO3 and I can turn it into anybody in that equation, but because the question wants O2, I'm going to turn it into O2. Moles of one thing to moles of another. To do that, we need a mole ratio. Where do I look for a mole ratio? Balanced equation. O2, if I look up, it has what number? 3. So what am I going to put there? 3. SO3, I look up. What number does it have? 2. So what am I going to put there? 2. And then we'll stop because that's what we want. We want moles of O2. So we shall stop. Now, I think this is the first time we've had numbers on the top and the bottom. Yes, maybe, probably. It doesn't change anything. The top is still multiplied, the bottom is still divided. So like, even though, yes, it's gonna be odd for a little while to have numbers on top and bottom, usually one of them is a 1. But with our coefficients, it's possible. But top is still times, bottom is still divide. So start with your 50, divide by your 80.06, multiply by your 3, divide by your 2. And I got 0.937. And we'll stop and we'll do the last one tomorrow. And then you'll just spend the rest of tomorrow practicing. Like this is one of those things, it's going to take some practice. Now, if you wanted